on. So tonight we have the great pleasure of having Dr. Dan Carney here with us for our resident member series to give us a new perspective on fundamental questions about observers. So Dan grew up in Cleveland, Ohio, and obtained his Bachelor of Science in Physics and Bachelor of Arts in Mathematics from the University of Cincinnati, writing his senior thesis in Tehran. He studied under Steve Weinberg, creator of the current model for the weak nuclear force and progenitor of the anthropic principles group at the University of Texas at Austin. He received his PhD in physics under the supervision of Wiley Fischler, who published a paper on the same topic as me 2 days before ours came out. But it's okay, I'm totally over it. Ours is way better. Don't let all these accomplishments in the field of physics trick you, though. Dan is a man of many talents, including the sport of getting hit by Asians with sticks, also sometimes known as kendo, incredible arm flexibility, an uncanny skill for moseying picked up during his time in Texas, an almost monastic resistance to the seductive beauty of string theory, and the trick to making flawless scrambled eggs. So please join me in welcoming Dan Carney.
Hi, so this is pretty exciting. I've never presented this material without using equations, so it was quite a trip to put this together. Some of this is really serious stuff. This is my thesis. A lot of it has what you might say are deep implications for different people, but I just couldn't resist having a lot of fun when I put this together, so I would encourage you to do the same. It starts off a little serious, and then it devolves into a lot of furry animals. One caveat, actually two caveats. So Charles told me that it's not always customary that people ask questions in the middle of a talk, but in physics it's considered kind of standard. You just berate me at will. In particular, I'm going to define a lot of words. If you get lost, if you didn't catch something, feel free to stop me. There's plenty of time. The other thing is I'm going to talk about physical systems in general a lot, and it's useful to just have something in your mind when I'm doing this. So you can pick anything. You can pick the microphone. You can pick a chair, a human, an electron. Doesn't really matter how big it is or how small it is. But just when I say something like a physical system has some property, it might be nice to say, okay, well, a chair has this property in the following sense, just in your mind. Okay, good. So, just to define what I'm going to talk about, I'm going to claim something kind of bold here and people could disagree with, which is that physics is about predicting outcomes of measurements. That's what physics does. It's not more or less than that. It should be able to predict basically any measurement, but it's not really talking about metaphysical questions about being and existence. So what I mean in particular is if I say something like, I'm going to describe some system, like your chair or whatever, what I mean is the following. I mean that I'm going to describe some set of measurements I can make, and then I'm going to give some formula for predicting the outcomes of the measurements. So this is, again, it's a little abstract, but you would say something like, okay, I have some model for this chair. The kind of measurement I can do is throw the chair through the window, and I can ask, does the window break? And then, with physics, I can predict the answer is yes. So this is sort of the blood and guts of what physics is about. Okay, so why do I need to get that out of the way? So let me give an outline for what I want to argue here. So you may think that observing something is a very obvious process. You sort of just look at it and then you can talk about it. Okay, in physics, you have to systematize things. You can put equations and meat on that. So it's taken a long time to do that in physics, actually, and it really only happened about 100 years ago. We cooked up this language called quantum mechanics. You probably heard about it, and you probably heard all kinds of mysterious-sounding stuff. And I'll describe it in some detail here, but what it really boils down to is just a way of describing measurements. So quantum mechanics is a set of rules for if you're going to measure something, how does the measurement work? What can you say? So quantum mechanics has been applied to basically two things. You could just break any system in nature into this kind of ridiculous dichotomy. There's two things. There's systems without gravity and there's systems with gravity. So for example, something out in the middle of space in vacuum is supposed to be something without gravity. Something in this room would be something with gravity. On the other hand, you can often give a good approximation to, say, the chair by ignoring its gravitational effect. The reason I make this split here is because if you want to describe these things with quantum mechanics and you want to describe the measurements you're going to do, we know how to do it in this case. In fact, we've more or less successfully described measurement of every system other than things involving gravitational fields. So quantum mechanics is remarkably successful. It always works. Okay. And then as soon as you start talking about systems with gravity, everything just goes haywire. So it's this really strange situation in physics where we certainly believe in gravity. It's certainly acting. It acts on everything. But we don't have any idea how to describe it in the language that we think is the one to describe measurement. So it's a big open problem to describe measurements involving gravitational effects, and that's one of the goals of my work. It's really the goal of my work. So there's a particular kind of problem, which is that in gravitational systems, sometimes you can't measure everything. So sometimes there's parts of space that you can't see. So if you've heard of a black hole, this is the canonical example. So if you have a black hole, what it means is that there's a part of space, which is the inside, that you can't see if you're outside. So as soon as you have that kind of a thing, we don't know how to apply quantum mechanics. We don't know how to actually systematically talk about measurement. So that might seem a little abstract or a little exotic. I want to make a point that it's not exotic at all. You sort of, in some crude sense, live inside of a black hole. More probably, you live inside of an event horizon. So here's how it works. What you can do is you can look at distant objects with a telescope, and you can measure both how far away they are and how fast they appear to be falling away from you. So in other words, if you look at the chair, it's not moving with respect to me, obviously, but if I look at the next galaxy over, it'll look like it's falling at some small speed. And if I look at a galaxy farther, it'll look like it's falling at some faster speed. That's all this says. So this is a very old diagram, actually, by Hubble. But it just says if you look out farther and you measure the apparent velocity of the object, it's going to be increasing with distance. And I guess anybody complain about that, but it should be. This is a paper from 1920 or something, so they didn't know. But what you can read off of this, I mean, this is amazing, I think, that you can extrapolate such a deep fact out of a linear graph. Okay, but what this graph implies, right? Well, if I go far away enough, the velocity will just keep increasing. Okay, so if something, so formally extrapolated, that means you're going to get something that's going faster than the speed of light on this graph at some distance. So that's confusing, right? And so what it means is that if you go a certain distance, objects will appear to be falling away from you at the speed of light, and anything farther than that can't send you a signal. There's no way for it to send you a signal and the light to catch up and hit you, ever. So you might think of the universe as this vast, infinite thing, okay? And what this is really telling you is that that's a very naive and not operationally meaningful statement. What it's telling you is that there is an edge of the observable part of the universe. It's about 15 billion light years away. So practically it's a rather large and vast universe, but okay, nevertheless it's finite. Anyway, for the purposes of the rest of this, what that means is that we live inside of an event horizon. So I'll describe that term in detail in a bit. So just put together, just to summarize that, what it means is that we don't have a theory that can describe all the measurements we can do. So to a physicist, that is just a totally unacceptable situation. Okay. And to me, it's a deeply unacceptable situation. I mean, it really means in a fundamental sense we don't know what we're doing in physics. So the goal here is just to explain what I just said in a little more detail. I'll draw some pictures and stuff. And I want to suggest a way of approaching the problem that is new. It is really odd that nobody has thought of this, in my opinion, but it's really only been developed in the past 20 years, and the idea is to really focus centrally on this notion of an observer. I should say what that's in contrast to, which is the standard dogma in physics, is that you imagine that there's objective reality. There's just, reality, and then you're looking at it. Okay, so first you have to give some description of all of reality, and then you have to say how you're looking at it. Okay, so that will lead to contradictions, and I'll show some of those later. What I'm suggesting is that instead you have to focus, you have to immediately say how you're looking at the system. You can't just say, here's reality, and then okay, as a side detail, I have to say how I'm going to look at it. I have to start by saying, I'm here, here's what I'm looking at, how do I describe that? So having a systematic theory of something like that is what I'm calling a theory of observation. Okay. Any questions? Okay. Everybody's down with that. All right. So let me step back. So I want to ask this question, what can physics say? This is just a reiteration of what I'm talking about. Since I'm talking to humanities people, I'm really excited I can quote a not physicist. So I found this deeply beautiful when I read it. Wittgenstein says, where, if you can't talk about something, then don't talk about it. So besides being eminently good life advice, this is just an excellent, precursor to what I'm trying to say here. So this is really what I'm going to argue for. You don't want to try to formulate stuff you can't talk about. If you can't get a signal from some system, why would you talk about what it looks like? Okay. So I want to give a review of different ways we talk in physics. A lot of the argument I want to give is almost a linguistic argument here, that you need to be careful how you say things. So how do we say things in physics? Okay, the old way of thinking about things, and I mean old from Plato to Newton, is something like this. We can, I fix some system, your chair or cat or whatever, and then we can just describe everything about it. No problem. We know everything. If you could do all the measurements and whatever, you're done. You can predict everything, you know everything. So Einstein made that a little bit sharper. He said, he implicitly said we can still describe everything about the system, but then there's a caveat here, which is you have to specify how you're measuring the system. You have to give a frame of reference. So you still have the complete predictive power about stuff, but you have to be a little more careful about how you describe it. Now you have quantum mechanics, which really messes with everybody's head. So what quantum mechanics says is you can't describe everything about a system. It's just not possible. It doesn't matter what system you're talking about, and it's not a statement about the way that you do measurements. It's just a statement about doing measurements at all. It is just impossible to describe everything about the system, in the sense that if there's some measurement that you think you can predict accurately, there's going to be another one that you cannot predict accurately. Okay, so that is really abstract. So let's apply it. Here come the line drawings and the animals. Okay, so I really like this picture because this is a spherical cat that I just Googled. I didn't even have to make it spherical. So, you can call this whiskers if you want to. Okay, so the ancient way of doing physics, what you would do is the following. Well, okay, you'd say, my system's a cat. Okay, how do I describe the system? So if you're a physicist, you skip right to this stuff. You say, okay, well, the state of the cat is described by position x, velocity v, and acceleration a, blah, blah, blah. So I'm drawing these things in symbols. Here's its position, it's located somewhere, it's going in some direction. Sorry, making the animations was too hard, so it's just going to have a V. And the thing is that in the old way of thinking about things, you can measure all of these observables as well as you want. So in other words, you can know everything about the cat. You can completely predict the entire future of the cat if you can measure it now. And if you know all of the equations for it. So that's good. Okay, so relativistic cats behave differently. So in relativity, you have to be a little more careful. Like I said, you have to specify a frame of reference. So in relativity, the way you would describe this is you'd have to start by saying, okay, there's some observer, he has some frame of reference. So, here's his rods that he's using to measure distances. So relative to the observer, the cat is at position X, it has a velocity V, and so on. And then you can start saying more. You can say things like, okay, there's some other observer who's moving with some velocity with respect to this observer, and with respect to this guy, the cat has position X prime, V prime, blah, blah. So you can go on and on and on. The point I want to make is that just the language has changed, right? Instead of saying just in the abstract, the cat has a position and a velocity, I have to say, with respect to somebody, or some reference frame, the cat has these properties. So you've already had to be a little more careful. Still, it's not a big extrapolation from the old way of thinking. Now you move to quantum mechanics and it just becomes crazy. So this is a quantum picture of a cat. It's an impressionistic picture, but okay. So now the language has changed again. I mean, it reads similarly, but it's very different. So now I say the cat is described by a state which has observable properties like the position, velocity, blah, blah, blah. But these properties behave very differently now. So, for example, if you know the value of the position, if you think you know where the cat is, up to some error, you don't know exactly where the cat is, then you could try to ask what is its velocity, and there's a statement in quantum mechanics that's deep and very troubling. I think when you first hear about these things, you can't predict the velocity very accurately. So if you know, this is the one equation, sorry, I lied in the email. If you know the position of the cat up to some error, so you know the cat is there, but maybe up to a millimeter or something because you're not sure, then you want to predict its velocity. Well, its velocity is very hard to predict. So the point of this equation is just if this is a small number, 1 divided by a small number is a huge number, so the error for the velocity of the cat is huge. So this is just what this picture is trying to convey. If you think you know the position pretty well, then the velocity has a big spread. It can go anywhere. So this is a famous thing. There's a famous physics joke about you tell the quantum mechanics professor that you located your homework so accurately that it just went off and just. Okay. So you can ask then, how do you put these things together? So the point of this talk is to sort of propose about something about putting together quantum mechanics and gravity has something to do with relativity. So you can ask just at the level I've described it, can you put quantum mechanics and relativity together? And the answer is yes, it's totally straightforward, so you just basically merge the sentences. So in quantum mechanics, you can't describe everything at once, and in relativity, you have to specify a frame of reference, so you just do both. Okay, easy enough. So just to go to town with this picture, this is a relativistic quantum cat, okay? So how would you talk about this thing? Well, you'd say, okay, I fix an observer, they're such and such place. With respect to him, I know the position of the cat to some error, and then I can measure his velocity to some other error, and likewise, some other observer can do the same thing, and so on and so forth. So I just put these pictures to make the point that you can do this. Putting relativity and quantum mechanics together is not impossible. It's been done. It goes by the fancy name of quantum field theory, but I like cats. So the trend is that you might think that in science, and in a lot of sciences it is the case, that as you progress, you can say more things. You learn more systems, and you can talk more about them. But for the history of physics, really, the trend has been that you can say less. You think you can say things, and then you find out that you can't. So you thought you could describe the position and the velocity to arbitrarily good precision, and you just can't. If you try, you'll get wrong answers. So what I'm going to talk about is continuing in this trend, no doubt. Okay, so I want to start talking about gravity. Before I do it, I have a very important rule in quantum mechanics: information is conserved. So that's a deep slogan. What it means is the following thing: information can't be lost or created. In particular, you can't witness it being copied or deleted. It just goes into another system. So what I mean by, are there questions? I feel like this is where I was really waiting for someone to be like, what's information? All right, well. So what I mean by this statement, thanks Charles, what I mean by this statement is that if you know the state of the system at some time, you should be able to predict it at some future time, and vice versa. If you know it at some future time, you should be able to go back in time and say what it came from. So let's see how this works out. So say you have the cat, and I'm going to look at how you can time evolve the cat. How can the cat go forward in time? So in relativity, we always draw time going up the blackboard. It's just bear with me. So, okay, you have the cat. This is the cat in its initial state. Okay, you can ask, what can it do? A perfectly good time evolution for the cat is to just continue being a cat. Okay, now suppose instead that you try to delete the cat. Okay, what happens? So you cannot just wipe a cat out of existence. Everybody knows this. You actually have to do something. So what would you do to delete a cat? A cat's a nice example because you can imagine all kinds of morbid things. So, suppose you blow up the cat, right? What happens? So the statement about information is that you have to be able to reconstruct the cat from the past if you can measure the thing that you make. So in other words, if you just delete the cat, so you had a cat and then you don't have a cat, you don't know how to go back in time because you don't have any information anymore, right? You had a cat that had some information and now you have nothing. So the rule says that that's not possible. Instead, you have to get something. So, for example, you vaporize the cat. What are you going to get? You get some gas, some thermal flux of stuff. And the point is that if you could measure all the properties of this thing, you could run this thing back in time and figure out that it came from a cat. Of course, it's a very hard problem, but this is helicopter level theoretical physics, so you can do it. The other thing you can't do is copy the cat. So suppose you tried. Okay, well, what's the problem then? The problem is, okay, well, I have one cat, now I have two cats that are totally identical. Well, so now I can't run that back in time because I don't know which cat came from the original cat. Okay, so again, you get the same phenomenon. You can't have the second cat. You can only have the one. Oops. That's fine. So in any case, this is just a funny illustration, but it's a very general rule that you can't copy or delete information in quantum mechanics. Gravity. So the idea is that in gravity, you might think that there are situations in which you can copy or delete information. So how does life without gravity work? So gravity determines how stuff moves through space and time. In particular, it determines how light moves through space and time. And in general relativity, you say that nothing can move faster than the speed of light. So basically, the gravitational field determines how all information propagates. So if there's no gravity, in particular, and you imagine that space and time just live forever, they extend forever, there's no cosmology, all this stuff is gone. If you could sit around and do measurements for a long enough time, anything that happened anywhere, you could see it eventually. So I'll draw this to make it more clear. But it's true. If you sit around forever, you'll see everything. So in other words, if there was information being copied by some process, you could see it. So it's operationally meaningful to say that, well, there's no copying, and that means that I can't see copying happen. Okay, so what do I mean by this? Okay. So this is a space-time diagram. So this is how physicists do things. So time, again, is running up. And I just write space. That's a little abstract, but bear with me. So, you can imagine space as one-dimensional. It's a ruler, for example, if you want. Nevertheless, here's you, or the XKCD guy, who is the observer. So he's labeled by O. And so let's talk about this guy observing cats. Okay, so here's a cat. So the way this should be read is something like, this is, say, you're in this room, which picks out a point on this axis, and you're here now, which picks out a point on the time axis. So that's now. And you think that there's a cat like over, in some other place in the green, and you want to know that it's there, okay? And in fact, what you want to do is do a measurement. So you want to shoot this thing with a light ray and get the light ray back to find out the answer. So you want to know, for example, how fast is the cat moving? So you use your radar gun, you shoot the cat with it. Okay. How does it work? So on these diagrams, light rays go in 45-degree angles. So what this means is, for example, if you're measuring things in units of light years and years, things will go, light goes 1 light year per year. But it's just a rule. You can keep in mind that light rays in my talk are always going to go at 45-degree angles. So this just means, I'm here, and so as some amount of time passes, the light ray gets over there, hits the cat, and then it bounces one back, and I get it. So this is how you make a measurement in space and time. The rest of what follows will generalize this picture, so if this is confusing, stop me. Okay. So let's time evolve the cat. Okay, this is the cat at a later time. This is perfectly fine, right? And I just want to make the point that you can check that this happened. The cat didn't change into a gremlin or something. And the way you would do it is you would just wait a little bit longer, send another signal to the cat, and get the answer. On the other hand, if something weird happened, so suppose you had one of these funny copied cats that I'm saying you can't have, the point I want to make is you could tell that this happened, and you won't always be able to do this when gravity's acting. So this is kind of maybe too obvious, but okay, if you wanted to check this, how would you do it? Well, you just send a signal, it would hit you back then, you get it back in the future, and then you could do this again, you could send a signal later, find out. You could measure the existence of this copied set of cats that violates the rules of quantum mechanics, your theory is out. So if you have a theory of physics that says I can copy cats somewhere, you're doomed. It's operationally ruled out. So in physics, it's going to be convenient to draw this a little bit differently. This is basically the same information. This is exactly the same information. What I've done now is I've just taken space and time and squished them onto a piece of paper. So instead of time running from, all the way from back in infinity to future infinity, I just run it, I just look at it, I draw it as a finite line. And what this diagram means is that, okay, here's where you are in space, you're just moving forward in time. And then you can ask, what can I see from the past? What can I see from the past? That's going to be the set of light rays that come at you like so. Okay, so this is the past, it's moving up in time towards you. So this is the edge of the diagram in the sense that you can, as I said, you can see everything eventually. So you can see, anything on this line will eventually hit you, so you can measure it. Likewise, what this one means is just the time inverse. It means if I want to send a signal out, where can I send it to? And the answer is everywhere. I can send it to anything on this line, just by sending light rays out like this. So in particular, if there's some objects in here, you can measure them just the way I did it before. You just send a light ray and get the answer. Okay, so now let's do a more interesting example. I'm hot, I have to take off my jacket. Excuse me. So what does gravity do? So gravity makes all that go haywire, basically. Like I said in the introduction, the point is that in gravity, if gravity is acting, it can be that you can't see everything. In particular, for example, in our own world, the presence of gravity implies that you can't see things beyond a certain distance. Okay, good. Here's a cartoon of the real world. This is a physics abstraction of nature. Here's you. This is the edge of the observable universe. And there's a bunch of junk in the middle, but I'm going to ignore all of that. So you can imagine some system, say a cat, which is out in space, actually quite near the event horizon. Anyway, you can imagine that there's some system out there, and you can ask, does it make sense for this thing to be copied? So for example, what would it mean if there's a copy of this thing outside your event horizon? Okay, so again, being outside your event horizon means that you can't actually measure this. Would it matter? Is it possible? So this is how you would draw this on one of these diagrams. So remember, if there's no gravity, the diagram ends here. Okay, but this diagram, you're going to have to take it on my word, but this is a correct representation of what we believe is the structure of the observable universe. And the difference is just that there's this extra triangle up here. So what does this mean? What it means is that there's some light rays that are coming at you from the past that'll hit you, okay? But then after you get to a certain distance, the light rays won't get to you. You just can't get to them. These are the ones that appear to be moving faster than the speed of light, according to you. So there's a part of space, or space-time, that you can never probe. You will never get a signal from this thing. Interestingly, you can send a signal to it. Okay, you can send a light ray and it'll get out there, but you cannot receive one. So what that means in particular, so you can ask something like, suppose the cat got copied. So if you say the cat got copied, that's supposed to be a violation of the rules of quantum mechanics. It violates fundamental physical law, supposedly. And I'm going to complain about the structure of the sentence, essentially. So it says, I said the cat got copied. Okay. So suppose it got copied out here. So, this cat was time evolving, and then some weird physics made a copy of it, and it's out here. Does it matter? Is it actually a violation of any physical law? And I claim the answer is essentially no. There's no violation. You would never measure anything that we believe to be true. You can't measure the fact that this cat was copied. You can't get a signal from it, just on the very simple grounds of the shape of this diagram. So people hem and haw a lot about things like in gravity information can be copied, and I want to just argue here that it's not obvious that means anything. So if you're worried about sort of a big picture of the universe, you might think it's troublesome, but nobody can actually check if it happens. So, you're kind of in murky territory. Does it matter or not? Okay. Let me do another example. Here's a black hole. Okay, so this is rather a lot like the previous one, right? So this is a cocktail hour trick you can show your friends. So the observable universe is like the inside of a black hole that you live in. A black hole is a little different. You live outside of the black hole, so you can't see anything in here now. This is a curvature singularity. It's described by Google Images. Okay, so suppose you have a cat outside. Again, you can ask a similar kind of question. What would it matter if a cat is copied and dropped inside? People, and literally many, many people talk about this for careers. So, this might seem facetious, but it's a real thing. So, people wonder about it. So it doesn't matter. And it's been proposed by people before me that the answer is not really. And the reason is the exact same as in the cosmological case. You can't tell. If you're outside the black hole, okay, so this diagram is a little different. It's not too important, the details, but the same basic idea. So you're here now. Again, time is going up, and you just start drawing pictures of cats. Okay, so these lines are the black hole's event horizon, and this red stuff is the singularity. So in other words, if the cat is going up in time and bangs into that, it dies. But until it gets there, it's fine. Okay, so this is where the space-time continuum rips, and all kinds of, we don't know what in the world is going on here. But we know pretty well, we certainly know what's going on out in this box, and we think we know what's going on in most of this stuff. We just don't know what's going on really close to the red. So in particular, we think that it makes sense to talk about light rays and things like this. So again, just the same point as before. Okay, my cat is hovering near the edge of a black hole for whatever reason. It's time evolving here. Suppose it's copied. Suppose a copy goes in. Or suppose, for example, that the cat falls in and the copy comes out. Is that a problem? And the answer is no. I mean, as far as I can tell, because of the simple observation that you can't tell. So you can see signals from this cat. It'll hit your world line. It can send you a signal. But the cat who's inside can't. I mean, just by definition. So the cat tries to send you a signal, but the signal just goes into the, through the wormhole or something. You can't tell that it was copied. It doesn't violate any observable principle in physics. So I want to make a comment on what this means. So again, I want to emphasize that to me this is actually a deeply linguistic problem. the problem that's usually stated is, suppose I have a black hole, a cat gets copied, that violates quantum mechanics, now I need to, invent string theory. So this is a little troublesome in my mind. I'm just giving Charles a hard time. That's not why you invent string theory, incidentally. So, hopefully. So, but the point is the sentence. The sentence says, a cat got copied. Okay. In other words, what you're implicitly doing, if you really get into it, if you just think about it, you're imagining objective reality is like a meaningful construct. You're imagining that like there is reality and the cat got copied as a sort of some statement about nature, and that sounds like it violates quantum mechanics. Oops, I did this in the wrong order. There we go. But if you just say it in an operationally meaningful way, if you just say, instead of saying the cat got copied, you just say, I saw the cat get copied, or you ask rather, did I see the cat get copied, or did Susan see the cat get copied, or whatever. You pick an observer, you say how they're measuring things, and then you ask a question that means something operationally in terms of an experiment you could do. And as far as I can tell, that largely fixes all these problems. There just isn't, it's just not there. Nobody in any of these diagrams can measure any of these supposedly paradoxical situations. You can't see the cat get copied. So although, maybe if, there's some kind of meta-observer of the system, or if you want to invoke something like God, it becomes very troublesome. Does God know that the cat got copied? I don't know, and I never will know, as far as I can tell. So in terms of doing physics about predicting outcomes of measurements, to me, that's the end of the story. You can't see the cat get copied. So if your description has a copied cat in it, but you can't check that, maybe you're fine.
Is the statement that nobody can see the cat get copied, or you can't?
Yeah, that's good. So I think the thing you need to say is nobody can see the cat get copied.
Including the cat.
Including the cat, huh? Well, if you copy the cat, which cat are you talking about?
So the cat can't be copied at a point, right? It can't be like a local.
The cat can't, yeah. That's for sure. Charles' point is that if the cat, if you copy the cat and you copy it right next to itself, then one of the copies could immediately check that there's a copy of itself, so that's just out. So it's so good. So that's a good point, actually. That's why gravity is really, this is fundamentally about gravity. If you don't have gravity acting, then no matter how far separated the cats are, they can always eventually check, for example, if there was a copy made. Okay, good. So what I've been working on, and my thesis is all about this, is just this question: Is there a way of doing physics in which you start by talking about an observer? You start by saying what exactly you're trying to do operationally. There is no known consistent mathematical framework for this. No one has it. You have one in general relativity, but you can only ask questions in terms of general relativity, meaning classical physics questions. There isn't a consistent mathematical framework that incorporates quantum mechanics. It's just not there. So in my thesis, I wrote what I would consider the first steps of something like this, but it's certainly not done. Then there's really a pressing question is, what are the experimental ramifications? So suppose you really did this. Everything here has been motivated pretty philosophically. Could you actually do an experiment where you could show that assuming objective reality is wrong? That would be wonderful, and we're thinking about some, but okay, we don't have anything here. But ultimately, what I'm really curious about is this question. I would really like to know the answer. Can you abandon the notion of objective reality and just build it up operationally? Do I have to imagine that nature works as some abstract entity or some real entity, whatever, and then sort of as a corollary, we're systems who are probing it? I want to know, can you actually go the other way? Can I say, okay, well, I'm an observer and you're an observer and there's some more observers, And we want to just communicate about all these measurements we're doing. And if we put all this information together in a consistent way, that is reality. Period. I mean, that is the operational meaning of reality. And really, that's what we do in science anyway. I mean, practically, you just make a bunch of observations, try to cook up a consistent picture. So these come in order of how they need to be done. So the answer to this is yes, that's my thesis. The answer to this is partly that's my thesis. The answer to this is we're not sure yet, but it requires this. And the answer to this is obviously requires all of this. So this is what we're working on. And I'll just end this with, I think, something that I found very moving when I read it. This is a restatement of Wittgenstein. So Heisenberg said, you must always remember what you observe is not nature, but just nature exposed to the way you're questioning it. Thanks.